Lagrangian for a charge moving in magnetic field. Our goal is to identify Lagrangian such that the equation of motion gives us the Lorentz force. The tricky part is that magnetic force depends on velocity, which means we cannot write this force as gradient of some potential. In order to proceed, we will require Maxwell equations. Let me write them out. Divergence of electric field is determined by the charge density rho. Divergence of magnetic field is zero. Curl of electric field is given by partial time derivative of magnetic field. Curl of magnetic field is determined by the current density and the changing electric field. In order to write the Lagrangian, we need to be able to represent fields in terms of potential. Well, we know how to do it in electrostatics. In electrostatics, the curl of electric field will be zero. Here we can use a fact from vector algebra that curl of a gradient is zero. In other words, we can always represent electric field as a divergence of some potential. The minus sign here is just a matter of convenience. Similarly, since the divergence of magnetic field is always zero, we can use another fact from vector algebra that divergence of a curl is zero. So that means that we can always represent magnetic field as a curl of vector potential. Let's denote it A. Now let's substitute this definition inside the third Maxwell equation, and then we can write that curl of electric field is given as partial time derivative of curl of vector potential A. Or, if we rearrange this, we can write that curl of electric field plus partial time derivative of vector potential A is equal to zero. So once again, using the fact that curl of a gradient is zero, we can equate this quantity in parentheses to a gradient of a function of potential. So this allows us to use the following definition. We can define electric field in terms of the gradient of potential. This is what we know from electrostatic, minus partial derivative with respect to time of a vector potential. Likewise, we define magnetic field as curl of a vector potential, A. The usefulness of this definition is that it automatically satisfies two of the Maxwell equations. Now we can write the Lagrangian. Consider the following Lagrangian. So this is 3D, coordinate and velocity. and it will be defined as kinetic energy minus charge times potential. And here comes the part that will be new to us. Velocity times vector potential. Up until this point, it looks just like the familiar kinetic energy minus potential energy. But then we have the additional term that, as you'll see, will be responsible for generating the proper Lorentz equation as equation of motion. Let's write it out in Cartesian coordinates. So for the first term, the kinetic energy will have mass over 2 plus the three components of the velocities, x dot squared, y dot squared, and z dot squared, minus charge times potential V minus so now we would like to see whether in fact we can recover the proper equation of motion. So let's first find partial derivative of Lagrangian with respect to position x. We will only prove the Lorentz equation for one component, the x component. So we will have partial derivative. The part that depends explicitly on x is potential v of x, y, and z, as well as time and vector potential x, y, z, and time. So therefore, we write partial derivative as q times partial derivative of potential with respect to x minus velocity x dot times partial derivative of a sub x with respect to x minus y dot partial derivative of a sub y with respect to x minus z dot and then partial derivative of z with respect to x. So this will go to the left-hand side of the Lagrange equation. Let's find partial derivative of Lagrangian with respect to x dot. So here we get from the first term, kinetic energy, we get m times x dot. And from the second term, the only term that survives is going to be this guy here. So it's going to be charge times a sub x. Now, to find the right-hand side, we have to find full derivative of time of this partial derivative, which becomes, the first term gives us mx double dot. In order to find full time derivative of the second term, we have to use chain rule, which will give us partial derivative of a sub x with respect to x times full derivative of x with respect to time, which is x dot. Same for y, and same for z. And we shouldn't forget partial derivative of a sub x with respect to time. So this is chain rule for full time derivative of a sub x, which is a function of x, y, z, and time. Now we can write what we get as the Lagrange equation. Now we can equate the left-hand side and the right-hand sides. Let's move this to the left-hand side, and it will be mx double dot equals, and here we will be doing some rearranging. So we will have this term here. It'll be minus q times partial derivative of v with respect to x plus this term here. Remember, since we moved the first term to the left-hand side, there will be a minus sign in front of this. So that'll be partial derivative of a sub x with respect to time. Then plus, now we go to this term as well as this term. And we combine them, and we can factor out y dot, and we get partial derivative of a sub y with respect to x minus partial derivative of x with respect to y. And now we include this term as well as this term. And we get minus q z dot, and then inside parentheses we get partial derivative of x with respect to z minus partial derivative of z with respect to x. Note that these two terms, this term here and this term here, are equal. So in fact, they are cancelled out. Now let's see if we can identify these parentheses. This one here, this one here, and this one here. Let's reproduce the definitions of electric field and magnetic field in terms of potential and vector potential. So we said that the electric field is the gradient of potential minus partial derivative with respect to time of vector potential. And for magnetic field, we said that it's a curl of vector potential. So then we can see that the first term is really nothing other than electric field with a minus sign along the component of x. So let's write out the curl of B will be given in terms of determinant of 3 by 3 matrix. So here we have unit vectors x, y, z. Then we have the differential operator ddx, ddy, ddz. And the components a sub x, a sub y, a sub z. And we're finding determinant. And so we can see that the component that will have partial derivative of a sub y with respect to x and partial derivative of x with respect to y with a minus sign will in fact be b sub z component. And the last parenthesis will be b sub y component. So you can see that just from writing the determinant. So this goes with plus sign, this goes also with plus sign, and this goes with plus sign, right? And the other permutations will go with a minus sign. Let's notice another thing here, that we can further simplify the last two terms. If we write V cross B, again, it's a determinant of unit vector x, unit vector y, unit vector z. Then we have component v sub x, v sub y, and v sub z. And then components of magnetic field b sub x, b sub y, b sub z. Okay. In particular, we can see that the cross product of v and b and its x component will be given by, so here we have with a plus sign, and this will go with a minus sign. So we're getting v sub y times bz minus v sub z times by. So thus we can simplify the equation that we got, and it becomes the following. So we're going to get the left-hand side, mass times acceleration in x times charge multiplied by electric field in X component plus the cross product of V and B along X component. So in fact we proved it. So this is the correct equation of motion. So let me reproduce this Lagrangian again. It's worth reproducing. So we have kinetic energy minus charge times potential minus velocity dotted with vector potential. So what does it mean? Other than we can write the correct equation of motion. Remember that we care about generalized momenta because they are conserved quantities potentially. So let's find generalized momentum. It's also known as canonical momentum. Canonical here means correct momentum. You'll see why. So for the X component, we simply have to take partial derivative of our newly found Lagrangian with respect to x dot, which we readily find to have mx dot. That part is familiar to us. That's usual momentum component. Plus, and here we have something unexpected, charge times the x component of the vector potential. In other words, our canonical momentum in 3D becomes mass times velocity plus charge times vector potential. So this is now a conserved quantity. In other words, mechanical momentum, as we know it, is not conserved in magnetic field, but generalized or canonical momentum is in fact conserved.